All right, last time we had started taking a look at the dot product, and just a real quick run through, we had discussed that the dot product took vectors and it made a scalar, and it had this kind of component-wise multiplication addition going on, and we had some properties of that, and which one was it? The angle between them, we did this fact down here too, the theorem 11.5. The angle that's happening between those vectors is the cosine of theta is the dot product divided by the two magnitudes multiplied. And we mentioned that the vectors are orthogonal when their dot product's 0. That's going to come back up in section 11.4. And we had seen one interesting scenario, or was it this one? Yeah, we were determining whether they were orthogonal or parallel. And I think this was the picture I left off on, but I hadn't written the definition. Does that sound right? That's where we were. Okay, cool. So we had this idea of projections, and that's where we were going to pick back up. So let me start with the definition for that. All right, so we're going to let U and V be two non-zero vectors. And moreover, you don't get to use that word very much, do you? Moreover, let the vector U have two components, W1 component and a W2 component, where W1 as a vector is parallel to the vector V, and W2 is orthogonal to V. Okay, and I had drawn this picture last time. We have these orthogonal vectors that we just described, and we talked about the fact that if this is our vector down here, I've changed the thickness since I was here last. If we have this vector V down here, and we have our vector U here that we are projecting down, it can be projected back down to, or can be projected down to the V vector, and then the orthogonal vector to V over here, we could also project onto it. And we have components. And so we have these two independent components that it's talking about, and it's labeling those as W1 and W2. Okay, so that's the picture that's going along with the description. So some vocabulary for what this is called. W1 is called the projection of U onto V, or the vector complement. I'm sorry, not complement, component. I was like, that doesn't sound right. Component of U along V. And it's denoted by projection of U along V, almost like you would see a subscript in a log or something like that, right? And secondly, W2 then. W2 is actually the vector U minus the vector W1. And this is the vector component of U orthogonal to V. So this is what it is. Let's talk about how you actually go about finding it. So this is theorem 11.6. Projection using dot products. If U and V are non-zero vectors, then the projection of U onto V is the dot product of U and V divided by the scalar, or not scalar, magnitude, I'm going to say the magnitude of V squared times the vector V. And obviously that all warrants an example so that we can actually use it, right? Or I could just let you do it on your own. Would you rather have an example?
How does that work?
How does what work?
Like, what's the proof for that?
I don't have it in my notes, but it is in your book. Yeah, it's there. So what you're doing is, I mean, you're basically doing unit vectors, right? But you're doing unit vectors in relationship to V. So if you take a look at, whoops, this part on the bottom, like just part of it, right? That would be the unit vector of V, correct? The other component is taking the U and the other part of it. So we've got this piece, and you're scaling back the unit vector, or the vector U, into making it a scale of the vector V. So that's basically what's going on. Yeah. And then you're projecting it onto the vector itself because you want the actual vector when you're done instead of a scalar value for it or something like that. So that's why you've got it multiplied over here by the vector V at the end. All right, let's try one. We're going to find, oh, this is part A too. Sorry, question 4, part A. Find the projection of U onto V, and on part B, we're going to find the vector component of U orthogonal to V. And I didn't write it down. U is the vector 2, negative 1, 3. And V is our vector 1, 2, 2. So we're going to first find the projection of U onto V. And in order to do that, there's several things we need. What do we need? We need a dot product. So I'm going to actually shift this down for a moment and do the dot product first. So my dot product of u and v would be 2 times 1, the first two components of v and u, plus negative 1 times 2, second components, and then 3 times 2, third components. 6 is it. Good job, Becca. Got a 6. What else do we need?
Magnitude.
Yeah, we might need the magnitude of v, and we need it squared, so really, we're just not going to have square root, right? I mean, the magnitude would have a square root normally, so, yeah, so how did you do it?
Actually, no,
I don't
it's
have,
9.
I have 9.
Yeah.
Okay, so it's vector v, and it's a dot product with itself, essentially, right? So if I take vector v and I dot product it with itself, that was probably really bad grammar. We would have, oh, I didn't mean to write it there either. Too much moving around my screen. I would have each of the vectors squared, right? Vector components squared. So I have 1 squared plus 2 squared plus 2 squared, which gives me 9. Yeah. Okay, cool. What's that?
We use, no, never mind, I'm sorry.
It's okay. So over here's the formula, right? How we're finding the projection. So I need a ratio of the dot product to the square of the magnitude. So the dot product was 6 over 9, and then times the vector v, and of course 6/9 is 2/3, yeah? And so we will multiply the 2/3 times the vector v. So I have 2/3, 4/3, 4/3. So that would be the projection onto the vector v. So how do I get the other piece, the component, the vector component of u orthogonal to v? Yeah, subtract it from what? U. Right, so our second component, they've called it W2. So in some sense, this is what we labeled W1 earlier, would be to take u minus W1. So my u vector is right here. And so component-wise, we're going to subtract the u vector minus the W1 vector. So what are we going to get? What's 2 minus 2/3? Here, I'll write them down so that it's all in one place. 2, negative 1, 3, minus 2/3, 4/3, 4/3. Hannah, did you give me the first component? Yep, it is 4/3 when I subtract. My second component's negative 1 minus 4/3. Not negative 5/3, because it's not negative 1/3, it's negative 1. Yeah, negative 7/3, good. And then I have 3 minus 4/3. That's 5/3, yeah. So these are our two vectors that we get for projecting onto V and the vector orthogonal to V. And of course, we do this all the time when we project things down and we think about like slope, like rise over run, right? It's how far right you go, how far up or down you go. Like we do this component kind of idea in 2 dimensions on planes when we think about slope all the time. But this would be for 3 dimensions and projecting on any vector, not just on an axis.